Welcome to this video on quantum chemistry. To briefly summarize the goal of quantum chemistry, let's look at the world around us. The world is, as we know it, is made out of chemicals and materials. And there's a lot of challenges related to chemicals and materials that could help the world become, let's call it a better place. For example, we could imagine we have better batteries, or maybe we could find a way to capture CO2 back from the atmosphere, or maybe we want to develop better medicine. All these challenges at some deep level relates to the chemistry of these problems. So we want to understand how this stuff works at a really fundamental level. A quantum computer can help us with that. And in this video, we will talk about how a quantum computer can help us solve some aspect of some of these challenges. Before we go into that, we need to show a little bit of math about what's behind quantum chemistry. So in chemistry, we work with molecules, and if you write up the physics of a molecule, we can write it in this Hamiltonian, which looks very abstract. But let's break it down. The first term here, where we have the differential operator with respect to the position Ri, accounts for the electron motion in the molecule. So each I represents a different electron. And this is really just the kinetic energy of each electron that we add up. The second term is interaction with the nuclei of the molecules. Each nuclei has a charge of Zk and a position of capital Rk, and interacts through the Coulomb interaction with the electron I at the position Ri. And the final term, which is actually the term that makes this whole thing hard to solve, is the fact that the electrons interact with each other. So the electron at position Rj interacts with the electron on Ri, and we have to sum up over all electrons that interact with each other. This Hamiltonian looks complicated, and we can make it look maybe slightly simpler by writing in this form. And the way we do that is through a technique called second quantization. What you do in this second quantization form is that instead of thinking about wave functions that you're trying to solve, you just pick a basis of some wave function that you like to calculate stuff with. And what you do is that you integrate up over these wave function, and you get these prefactors, which are really in just terms from the previous slide. So the first term here is pq, and integral over wave function p and wave function q over the motion of the electrons and the nuclear interaction. And this HPQRS is a fourth order term that comes from the electron-electron interaction and relates to the wave functions p, q, r, and s that we integrate up over. And then we can create electrons in these wave functions through these fermionic creation operators. Here you can think of it as if you are in the vacuum and you apply a p dagger, you create an electron in vacuum, and if you apply a p, you annihilate an electron if it was there already. Keep in mind these are fermionic operators, meaning they have different commutation relation than, for example, the annihilation and creation operators that you know from the harmonic oscillator. That makes it tricky if we want to go and solve this on a quantum computer, because on a quantum computers we don't have electrons, we have qubits. So we need to map from electron operator to qubit operator. A very standard way of doing that is called the Jordan-Wigner transformation. There's also other transformations, for example, the Parve-Kitaev transformation, but we will not discuss that in this video. The way the Jordan-Wigner transformation works is that you take a product of set operators for the first p-1 qubit, and then you multiply it by the sigma x and sigma p operators for qubit p. And this way, these product operators of qubits now behave like they were fermionic operators. So we can take these two expressions and just plug it into the Hamiltonian above to give us a qubit Hamiltonian. Okay, now we have a qubit Hamiltonian. So how can we use that to solve our quantum chemistry problem? What we do is we want to find the ground state energy of that Hamiltonian, and we can use a technique called quantum phase estimation for that, which is an algorithm that we can run our quantum computers. The first thing we do is we take a register of k qubits, which are unrelated to the chemistry problem, but relates to how precise can we measure the energy. And then we create an approximate ground state of the Hamiltonian. This we can generate, for example, using Hartree-Fock techniques with our classical computer. The number of qubits that encodes this ground state should be equal to the number of orbitals that you looked at when we wrote the second quantization form. Now with the register qubits, we put them all in an equal superposition with this Hadamard gate, and then we apply a controlled unitary. This unitary is the time evolution for some time delta t that we choose ourselves to run the algorithm with the Hamiltonian h. The way we then do these controlled operations is for the first qubit in the register, we just do a controlled unitary. For the second, we do a controlled unitary squared, and so on until we get to the k qubit, where we do the controlled unitary to the power of 2 to the power of k. The challenge is to construct these controlled unitaries well, but if we can do that, we can then at the end do a inverse quantum Fourier transform. This is the same type of inverse quantum Fourier transform that you would use in Shor's algorithm that you saw in a previous video. And then finally, we measure all these register qubits in a way that gives us a binary representation of the energy of the Hamiltonian of the ground state. Of course, it gives actually the phase. That's why it's called the quantum phase estimation. But we know delta t, and we can then get the energy as the phase divided by delta t. So this circuit that you see here is really the key workhorse of quantum chemistry, and the one that can help us solve all the interesting problems that I talked about in the beginning. And with that, I want to conclude with the message that quantum computers can help us to find ground state energies of molecules we care about. And this is actually the most promising application in the sense that this is an application where we really know that quantum computers can do something useful that with very high certainty. Except it's very hard to construct these circuits, so there's still a lot of research going on in doing it well. An example where people did it for small molecules is the reference that I put here, done by the Google AI team, where they demonstrated that they can calculate the energy of a molecule that depends on how it's rotated.